here in this video, we will see what is Macaulay's method and how it is to be used. So let us get started. Macaulay's method, it is also called as double integration method. This is the other name of Macaulay's method. It is also called as the double integration method. Next, in this method, a section is taken extreme far away from the left hand support. So in Macaulay's method, we have to take a section at extreme far away from the left hand support of the beam. Then in this, a systematic calculation of bending moment is done at the section. Next, in Macaulay's method, we use the double integration concept to get slope and deflection respectively. So in Macaulay's method, we use the double integration concept to get slope and deflection respectively. Next, here let me explain that with the help of a diagram. Here I am considering a simply supported beam having length L. Then on this simply supported beam, there are three loads. I am just taking this example that there are three loads, W1, W2 and W3. All three are point loads as we can see here. Next, the distances of the load are W1 is located at distance A1 from the left support, W2 is located at distance A2 from the left hand support, and W3 is located at distance A3 from the left hand support. Now suppose for such a beam which I have drawn here, we need to find out the slope and deflection at various points by using Macaulay's method. Then the steps would be, so I am going to write the steps in Macaulay's method. And the steps are, first is calculation of support reactions. That is, first we are going to find the support reactions. At A it is RA, at B it is RB. So first we will get the value of support reactions, that is RA and RB. Next, after getting the support reaction, we will take a section XX at the distance small x, which is small x, from left hand support. So here left hand support is point A. So from point A we will consider a section X extreme far away from the left portion. So suppose I am taking the section here that is extreme far away from A and just before B. So this is the section XX located at a distance small x. Now when we are using the Macaulay's method, the first thing would be taking moments about section XX. So here I'm going to take the moment at this section XX, and for that whatever are the clockwise moment I'll treat them as positive and anti-clockwise moment I'll take them as negative. So taking the moments, moment at XX will be equal to clockwise moment RA into X, that is positive. This is the first section. Next, W1 will produce anti-clockwise moment. Now the distance between XX section and W1 is X minus A, because X minus A1 will give us the distance between W1 and section XX. So that is minus, because it produces anti-clockwise moment, W1 into X minus A1, the second section. Next, W2 is also producing anti-clockwise moment, and the distance between XX section and W2 is X minus A2. So it is minus W2 into X minus A2. Then after this, W3 is producing anti-clockwise moment, so again negative, minus W3 into the distance between W3 and XX section is X minus A3, X minus A3. So now once we get this bending moment equation, this bending moment at XX can be made equal to EI d square y by dx square, because we can write the bending moment at any section by using this formula. We can replace moment at XX by EI d square y by dx square, and this term I will copy it as it is. Now once I have reached here, I have completed the third step. Now in the fourth step, integrating the bending moment equation, once we get so now integrating the bending moment equation, we have here the bending moment equation. I'll call this as equation 1. Now integrating this, on the left hand side I have EI, it is a constant, I'll keep it as it is. EI is a constant. Next, integration of d square y by dx square, that is dy by dx, is equal to, now Ra will remain as it is because it is a constant value. Integration of x, that will be x square by 2, plus C1, that is the constant of integration. This will be our first term. Next, minus W1 will remain as it is, constant. Next thing is, this bracket will be integrated as a whole. So x minus a1, that will become x minus a1 whole square divided by 2, the second term. Then minus w2 will remain as it is, and x minus a2 will become x minus a2 whole square divided by 2. At last, minus w3 x minus a3 square whole square divided by 2. So here I have integrated once. I'll keep this as equation number second. Next, the fifth step is integrating equation 2, again we get, now I am in case of Macaulay's method, once we get dy by dx, this dy by dx represents slope, that is the angle by which the beam has been bent. So once we get dy by dx equation, which is from this we will be getting the slope equation. Now we have to integrate the slope equation to get deflection. So I am integrating this equation number second. So here we have ei dy by dx integration is y, ra will remain as it is, this 2 will be written here, x square integration becomes x cube by 3 plus c1 into x plus another constant c2 because I am integrating it twice, next minus w1 by 2 x minus a1 whole square, so integration becomes whole cube divided by 3, the next term minus w by 2 x minus a2 whole square becomes whole cube divided by 3 minus w3 by 2 x minus a3 whole square integration becomes whole cube divided by 3. So therefore ei into y is equal to ra, 2 into 3 that becomes 6x cube plus c1x plus c2 minus w1 upon 6 x minus a1 cube, similarly w2 by 6 x minus a2 whole cube minus w3 by 6 x minus a3 whole cube. So now here also we have an equation, I'll call it as equation number third. Next, if we look at equation second and equation third, in both the equations we are having constants. In equation 2 we are having c1, in equation 3 we have c1 c2 both, so we need to find these constants. So the next step would be step number 5. In step number 6 we are going to find the constants by applying boundary conditions. So by applying the boundary conditions we will have to find the constants, and if I look into the diagram, the boundary condition is when the distance x is 0, here deflection y is 0. So the first boundary condition would be at x is equal to 0 y is 0, and the second boundary condition is at x is equal to capital L, at x is equal to L, y is again 0, so deflection is 0. So after reaching here, the next step would be we would be putting, that is in equation 7, applying boundary conditions in deflection equation 1 at a time to get constants C1 and C2. So once we know the boundary conditions, we can apply them or put the values in the deflection equation, which is equation number 3, to get the values of C1, C2. And once we know C1, C2, that is step number 8 in Macaulay's method. Once C1 and C2 are known, then put their values in equations 2 and 3 respectively. That is, once we know C1, C2 values, first we are going to put the C1 value in equation number second, and that will give us the slope equation. Then C1, C2 values we will put in equation 3, that gives us y, that is deflection equation. So Once C1 and C2 are known, we can put their values and in equation 2 and 3 respectively. Hence, we will get the slope and deflection equation respectively, and from them we can calculate slope and deflection at any point in a given beam. So once we get, after putting the constants C1 and C2 in equation 2 and 3 respectively, from equation 2 we will get slope equation, that is dy by dx, and once the constants are known, we know the value of Ra. Just we have to shift the distances, and once we shift the values of x, that is different values of x, we will get the different values of slope. Similarly, we can get different values of deflection from equation 3. So here in this video we have seen how to use Macaulay's method, what is meant by Macaulay's method, and by using the double integration method we can get slope and deflection for a given beam.